Welcome back. Today we're going to start by talking about a special kind of filter called an all-pass filter. So, an all-pass filter, in its simplest form, has a transfer function that looks like this. Z to the negative 1 minus a star over 1 minus a z to the negative 1. So, as an all-pass filter, as the name suggests, this filter passes all frequencies, but it has some interesting characteristics with the phase. So let's first look at the magnitude response and see how that works. So if we look at, let's put in e j omega and look at the magnitude squared, we get this by multiplying h of e to the j omega by h conjugate e to the j omega. And as a reminder, if you have a function that involves, maybe it's a nonlinear function of complex variables, how do you find its conjugate? You just go hunt down each one of those imaginary numbers or complex numbers and find the conjugate of those. That's all that's needed. So in this case we have h and h star, like so. So now it's a little bit of algebra. We just multiply this out and we get 1 minus, now we're going to have a star e j omega plus a e to the negative j omega plus magnitude of a squared all over 1 minus a e to the negative j omega plus a star e to the j omega plus, you get it, a squared. And the tops and the bottoms are just the same. And so now we have that the frequency response, magnitude squared, of an all-pass filter is just equal to 1. Okay, this filter has complex values in it. We have a star and it's assumed that we have a complex a. It could be real, but that's just a special case. What happens if we want a real all-pass filter? We can get that simply by putting in the conjugate points. So all-pass filter would give us, we would have z to the negative a minus a star times z to the negative 1 minus a 1 minus a z to the minus 1 and 1 minus a star z to the negative 1. So what's really interesting is where are the poles and the zeros with this type of a filter. So just looking at the first term here, or I guess at the all-pass filter with one pole and one zero as defined above, this says we have a pole at A so there's a pole. I guess we should mark that with an X, which we use for poles. What about the zeros? The zero is at 1 over a star. So where is 1 over a star? Well, let's express a in terms of a magnitude and a phase. then A star is going to have the same magnitude and an opposite phase. And 1 over A star is going to be 1 over magnitude of A with the same angle. So it may be a little bit counterintuitive at first, but that essentially means that our 0 is out here at the same angle, in this case theta, from our example below. So we have these a pole and a 0 lined up, and one is 1 over the magnitude of the other. And when we add in our second term right here, that's going to give us an a pole right there and a 0 right out here. So essentially what's going on is, as we go around this circle to find our frequency response, the impact of the pole and the 0, the way they're placed, are always going to perfectly cancel each other out. But the phase impact of the pole and the 0 are different. And so an all-pass filter will have a uniform frequency response, but the phase response is going to experience a sharp change as we get near those poles and zeros. The closer the pole and the 0 are, respectively, to the unit circle, the sharper that change is going to be. So here's an example of a all-pass filter, and it was created using this code. Let's paste it in there from MATLAB. So in the upper plot we have the magnitude, h e to the j omega. In the lower plot we have the angle. Now if you look at the code, you'll see that I use this MATLAB function called unwrap. Unwrap lets you take the angle, which is normally returned between minus pi and pi, and it tries to make it continuous so that you don't have these discontinuities that would otherwise show up as it tried to maintain a principal angle. Here's where you defined A. So in this case, A is equal to 0.8 e to the j pi over 3. And that's actually similar to what we showed up here, only 0.8 would be a little bit closer to the unit circle. And you can see that right at pi over 3, or the frequency where our pole and 0 lie, is where we have the strongest phase change. As we move far away from there, it's linear with a very small angle, almost flat. So that's an all-pass filter.